Hi, welcome back. We are working on applying the properties of the continuous time Fourier transform. So before we begin, let me just tell you again, or lucky you, that you do not need to know circuit analysis in this course. Anyway, what we're doing here is finding the output of the low-pass RC filter when the input is this thing x of t. So let's be concrete here. We've got a signal that looks like this. It's 0 and then it decays like this. Okay, and that decay is given by e to the negative 2t over rc, and we're going to call that x of t. That's the input. And if you feel like that's contrived or that's kind of a textbook example, it kind of is, but also kind of not, because this signal, this type of signal, this decay can come from an RC circuit in itself. So this can come from a resistor capacitive circuit as the capacitor discharges. So now we're going to take that signal and we're going to send it to an RC filter. Okay, and the RC filter we've talked about in the past, and it is a linear time invariant system. So the idea here in signals and systems is that we're not going to analyze the circuit. We're going to use its mathematical properties, being linear time invariant, and its impulse response and frequency response to figure out what we get out of the circuit. Okay, and we've said before that the impulse response is 1 over RC e to the negative t over RC u of t. So we said that in a previous video. That was the result. And the Fourier transform of that is the frequency response. And I'm going to apply this Fourier transform pair from a table, and we've also actually proved that pair before. And so this is 1 over RC times then the transform of this thing is 1 over j omega plus 1 over RC, right? A here is 1 over RC. And so this is the frequency response of the RC low pass filter. And so what we're trying to do is get y of t. Y of t. Now, I want to point out, in the first half of the course, we were using convolution and we were doing all of this analysis in time before we got to Fourier and frequency. That still applies. So you could, and it would be a good exercise, I would encourage you to try it, you could convolve x with h. Take this waveform, convolve it with h, which is a similar looking waveform. Do the convolution, and then you have y of t. Okay, that still applies. The output of a linear time invariant system is always the input convolved with its impulse response. However, we're going to use a different method in this video. We're going to use the convolution property. The convolution property of the Fourier transform. And that says that if I have a signal that is the convolution of two signals, then its Fourier transform is the multiplication of the individual Fourier transforms. So here, if I apply that, the output spectrum is the input spectrum times the frequency response. Okay, that's the idea. So that's the convolution property. I'm going to just put that in a box, list all the properties that we're using. And so let's get started. I have capital H, right? Here's capital H, so I need capital X. Well, my input is this thing, right? And that seems to be related to this Fourier transform pair that I have up here. And so we can get X's Fourier transform rather quickly by using this pair and noting that A, if I just compare, right, I form fit, I see that A is 2 over RC. So then I know that x of t has a Fourier transform 2 over RC. Look at that, and I didn't even have to use the analysis equation at all. So now I've got capital X. We're going to call it capital X. So if I wanted y, then all I have to do is y of j omega is equal to the multiplication of those two things. So this is 1 over 1 over j omega plus 2 over RC, that's x, times the frequency response, 1 over j omega plus 1 over RC. And the common denominator is the fraction, is the two terms multiplied together. Like this. Okay? Now we're kind of stuck because we're after the signal y of t, and we have the signal's spectrum, capital Y of j omega. So what we need to do here is take the inverse transform of this thing to get back y of t. Well, we consult our table and we don't have anything that's in this form in the table. Also, using the synthesis equation or the inverse Fourier transform equation on this thing is going to be pretty rough. What we would like to do is separate those two factors by finding a constant, where I could have a constant over j omega plus 2 over RC, that's one of the factors, plus another constant b, j omega plus 1 over RC. I left off, by the way, a 1 over RC here. This should be, capital H has a 1 over RC. 1 over RC. Okay, so let me back up. 1 over RC times this. Okay, so again, I would like to split up those fractions. And this is like, usually we go the other way by getting a common denominator. Like if we wanted to add 1/2 plus 1/3, the common denominator here is the multiplication, 2 times 3, and so this would be 3/6 plus 2/6 is 5/6. But we're going the other way now. We're taking the 5/6 and we're breaking it up into its two factors, right? And we need to find these coefficients in the numerator. Do you know what that's called? You've seen this before in your math courses. That is called partial fraction expansion. So I'm just going to write that here. Partial fraction expansion. So this is partial fraction expansion is kind of interesting because it's something that we're going to need actually for the remainder of the course. And I'm going to go through it kind of quickly here, but we'll come back to it later. And it's interesting because I have a different method than students learn, it seems. And I'm going to argue that my method is better and it's faster. However, ultimately, I'm not concerned with the way you solve partial fraction expansion as long as you can do it. I don't care. So, but I will try to convince you that my way is better. Alright, so we need to figure out what A and B are. So I'm going to take this equation that I'm going to box in orange, right? And it's an equation. And I'm going to multiply everything by A's denominator. And also cancel the 1 over RC's. So I'm going to multiply everything by A's denominator. And so on the left, I have 1 over j omega plus 1 over RC. So by the way, I should say this is to find A. Multiply by A's denominator. So I have 1 over j omega plus 1 over RC because this factor cancels, equals, then I have A plus B times A's denominator over B's denominator, like that. And then, this is an equation in omega, j omega. And an equation has to be true for all values of its variable. So I'm going to strategically choose a value of j omega, not just omega, but j omega, because we're really considering j omega to be the variable. J and omega, they're like peanut butter and jelly. They go together. And I'm going to choose j omega is equal to whatever that makes a's denominator 0. Whatever makes a's denominator 0, which would be negative 2 over rc. So the reason I'm doing that is because, and I'm showing you the details here, but really this could be done in your head, or at least it can be done in my head. When I let j omega equal negative 2 over rc, b's contribution goes away, right? Because I have 0 over something non-zero. So then I'm left with just a on the right. A is 1 over, and then j omega we're letting be negative 2 over rc. So negative 2 over rc plus 1 over rc is negative 1 over rc. So a is negative rc. Perfect. Now, we're going to do the same thing for b, right? So let's do b. So let's summarize what we did with a. We multiplied by a's denominator, and then we set j omega equal to whatever makes a's denominator 0. So I'm going to try to do the same thing with b, and I'm going to try to do it without writing too much down. So multiply by b's denominator, okay, and this is after canceling the 1 over rc's, and then set j omega to be equal to negative 1 over rc, and what I get is b equals 1 over 1 over rc. And so b is rc. Okay, so like I said, I can do most of this in my head, and I encourage you to practice this, and eventually you'll be able to do it in your head. And so you can check me on that though, but b is rc. And so now we can write y, capital Y, as 1 over rc times b was rc over j omega plus 1 over rc. A was minus rc over j omega plus 2 over rc. Okay, so notice the rc's cancel, and we're going to take the inverse Fourier transform of that. We're going to use this Fourier transform pair, and we're going to use linearity. Let's talk about linearity first. Linearity allows me to take the inverse transform of each piece separately. So after canceling with 1 over rc, this first piece is 1 over j omega plus 1 over rc. So that looks like this, with a being 1 over rc. So it has an inverse transform, negative t over rc, u of t. Okay, now again, linearity allows me to look at the second piece separately. After canceling with the 1 over rc, this is negative, right? And then I form fit this with this guy, and it looks like a is 2 over rc. So this is negative e to the negative 2t over rc u of t. That's y of t now. We took the inverse transform, and I can clean that up a little bit and factor out the u of t. So this is negative e to the negative t rc minus e to the negative 2t over rc u of t, and that is the answer. No convolution required, right? Instead of convolution, we use the Fourier transform.